And to make the example of a category coming from a partially ordered set even more explicit, let's consider the case where P is the power set of the set with two elements, 1 and 2. So this is the set of all subsets of this two element set, and it's partially ordered by inclusion. This then gives rise to a category with exactly 4 objects. The empty set gives rise to an object. The two one-element sets, 1 and 2, give rise to an object. And then there's the set with elements 1 and 2. And it's convenient to draw all non-identity morphisms in this category like this. So there's an inclusion like this that gives rise to a morphism. There's an inclusion like this that gives rise to a morphism. And it's also this way. This is then, in fact, commutative square, because these two composites are both the morphism associated to the inclusion of the empty set in this set of with two elements. And it's often convenient to draw diagrams to draw small categories with diagrams like this. And it's also very common in this case to not draw the identity morphism. So I could also denote them like this and draw also in this composition, but this makes the diagram already more difficult to digest. So the previous version without these additional morphisms is a more common one to denote this. I'll continue with a few more examples now with a little bit less details. So another category you may have encountered is the category of topological spaces. So topological spaces are the objects of these categories, and the morphisms are the continuous map. So this is a category that's commonly studied. It has a counterpart that we'll see again in a minute. So that's the category of base topological spaces. This means topological spaces with a preferred base point and base point preserving continuous maps. This is also an example of a category. And then there's a third example that belongs to these. And that's the so-called homotopy category of topological spaces. So the objects are still topological spaces, but now the morphisms are not continuous maps, but rather equivalence classes of continuous maps, modulo the equivalence relation homotopy. So the morphisms are homotopy classes of continuous maps. And I'm mentioning this last example to highlight once more that category is not always objects set with additional structure and morphisms, maps of set that preserve this structure, because in this example we see a homotopy class of maps that's not a set, that's not a map of sets that respects additional structure, but rather an equivalence class of these. So this is, again, highlights this phenomenon. So the next thing I would like to introduce is the notion of functor. This is something that can relate to categories, and in some sense one can say that the notion of functors is even more important than the notion of categories itself. So here comes the definition. We have to stop. Sorry, I made some